Now I want to take time to take a look at a different type of integral. What you have seen most recently is something known as a definite integral. And the way that is written, a definite integral is written integral from a to b, with the a and the b being the limits of integration of a function f of x. And again, for now, the dx simply means that x should be treated like a variable and nothing else should be treated like a variable. With a definite integral, once you complete a definite integral problem, what you will get is an answer, pure and simple, that is a number. That is all a definite integral can give you, is a numerical value. Now, the meaning of that number is a discussion within itself, and we've already talked about it. There's already been some discussion of that. It can be area under a curve, it can be net area under the curve, etc., but it's a number. We're now going to look at something known as an indefinite integral, and the notation does not change drastically. When you write an indefinite integral, it'll look just like the definite, except the limits of integration are omitted. All right. And if you evaluate that, what you will get is a function, or actually more exactly stated, you get a family of functions. And I'll show you what I mean by that soon. All right. In other words, integral of small f of x dx equaling large f of x, what that implies is that if I take the derivative of the large f, I get the small, and that's a double implication, by the way. All right. So again, when you integrate with limits of integration, that's a definite integral, you get a number. A indefinite integral gives you a function, and it is the function that when you take its derivative, you get back what you're integrating. For the time being, when we do this type of integral, when we complete this kind of integral, what we will be relying on is all the derivatives that we've taken before. Now, what you will find in your textbook, let me just lay this here for you. What you will find in your textbook and in different places, you're going to find tables that are going to give you the answers to certain integration problems. But is this type of table absolutely necessary? Well, not really. For example, integral of e to the x, you should already know is e to the x, because you know the derivative of e to the x is e to the x. The integral of secant squared shouldn't have to be given to you, because you already know that the derivative of tangent is secant squared. So if you just take all of the derivatives that you have memorized in the past and reverse them, so to speak, in your mind, inverse them would probably be a better way to put it, then you know all of these integrals already. For example, you know that the derivative of natural log of absolute value of x is 1 over x. So this integral shouldn't be a surprise to you. All right? So if you've memorized the derivatives appropriately, then none of those integrals should be the least bit new to you. There's also a convention, sort of an accepted practice. If you say, what is the integral of 1 over x squared dx? If you were to say, well, that's negative 1 over x, well, you should realize that 1 over x as well as 1 over x squared, those are undefined at 0. So the assumption is that this is a valid equality as long as you stay away from 0. And also, you'll find if you're 1 over x squared, if you were to sketch it versus sketching negative 1 over x, all right, what you'll see is that the behavior is different on the left-hand side versus the right-hand side of 0. So another convention is that this large f, which is your integral f, is equal to 1 over x plus one constant, plus a constant when x is less than 0, and it's equal to 1 over x plus a different constant when x is greater than 0. So these are just things that we accept. These are conventions we just follow. All right. And you'll notice that there's a plus c here. Another convention, another accepted practice is when we complete an integral of this type, when we complete an indefinite integral, we want our answer to be not just a function, not just one function that was the antiderivative of the original, but something that represents all functions that are antiderivatives. So there's always a plus c that's placed on there so that this will fit any function that works in this equation. And that's why I say that when you take a definite integral, you get a numerical answer. And when you take an indefinite integral, you get a function answer. And it's not just a function, it's a family of functions. And they all are related by the fact that they differ from one another, but nothing more than a different constant. So when you're doing an indefinite integral, you must always remember to put that c on there. And that actually brings up a interesting point with your definite integral. With your definite integral, we are in the practice of not putting the c on there, but it would still work if we did. All right, you could put that c on there. If you want to look at just an easy example, if you wanted to integrate something very straightforward, like an x dx from maybe 1 to 3, well, if you integrate the x, you got to bump the power up by 1 and then divide. All right, and then if you felt inclined to put that constant on there, even though we've said you don't have to, all right, if you felt inclined to do so, when I evaluated this from 1 to 3, what would happen is when I put in the 3, I would get a 9/2 plus c. And then when I put in the 1, I would get a 1/2 plus c. 9/2 minus 1/2 is an 8/2, which is a 4. And a c minus a c means the c's just cancel out. So with the definite integral, if you put the c in there, it would have no impact whatsoever. The c will always cancel each other out when you evaluate, which is basically why with the definite, we don't bother. Okay, we just say it's okay to leave the c out. Don't let it bother you. Ignore it. But that's only for the definite. For the indefinite, we always have to have that constant of integration. So we're representing every function whose integral is as shown. All right. Again, for now, for the moment, we don't have any really fancy tricks or techniques that we can use. We just have to integrate things based upon what we know of derivatives. For example, an indefinite integral of square root of x cubed plus cube root of x squared dx. What we would need to do to make this look like something that's closer to a familiar derivative format is rewrite this as x to the 3/2 plus x to the 2/3. We do this because we have a power rule that we can use. So 3/2 will bump up by 1 and become 5/2 and multiply by 2/5. 2/3 will bump up by 1 and become a x to the 5/3 and then multiply by 3/5. And again, don't forget that constant of integration. An indefinite integral is incorrect if you don't have that constant of integration. All right, if you had something of the nature v times the quantity v squared plus 2 square dv, since I have a product here, I can't integrate this as it sits. There will be a technique, there'll be a trick that we use later for that. But at the moment, I can't do that because for integration, I have no product rule. I have a product rule for taking a derivative. I have a quotient rule for derivatives. I have no product rule or quotient rule for integrals. And to be honest with you, you never will. That's not something that's ever going to happen. It doesn't exist. So what I have to do, and the one thing a very important thing you have to remember is you know how to do algebra, and you're going to have to do a lot of it. So I'm going to square this thing out. That will give me an AV to the fourth plus a 4V squared plus a 4. And then I'll distribute V times, well, let me just go ahead and not write it again, just go ahead and do it. V times the V to the fourth will be a V to the fifth. That'll be a 4V cubed plus a 4V. And again, the dV is telling us treat V like the variable and nothing else. Integrating V to the fifth, you get a V to the 6 over 6. And then the V to the third would be a V to the fourth over 4, which would mean that 4 that was already there would cancel. And this would be a V squared over 2, but the 4 over 2 would be a 2. And don't forget the constant of integration. All right. So again, a little bit of algebra made that one workable for me. Algebra is not the only thing you'll need. You'll need to remember what you know about trigonometry. For example, if you have sine of 2x over sine of x dx, I've got two problems here. First of all, I have a quotient. That's a big problem. And I have no quotient rule. And these two arguments don't match. One of them is a 2x and one of them is an x. But again, if you remember your trig, remember sine of 2x is 2 sine x cosine of x over a sine of x dx. With that one, the signs cancel. The 2 can be thrown out front. So all I have to actually integrate is the cosine. All right, so the 2 will come into my answer. All right, and when you integrate cosine, remember, derivative of sine is cosine. All right, so this will come back to a sine of x, again, because derivative of sine would give me the cosine, plus a constant of integration. Never forget that constant of integration. And technically, even though this may be too technical, all right, this may be looking at it too closely for the moment, but when you multiply the 2 through here, technically speaking, that changes the constant. And I just wanted to introduce you to that here a little bit early, the fact that when your constant changes, we acknowledge that by putting a subscript to say, hey, this isn't the same constant as it was before. Again, at this moment, that is a pretty small, a pretty insignificant technicality, but it is still the case. All right, so you're going to have to get accustomed to dealing with both your indefinite and your definite integrals. You're going to see them mixed together. Just in a single homework set, you might see a few of both. All right, so for example, as soon as you finish those, you might get hit with something like integral of from 1 to 2 of a y plus a 5y to the 7th over a y cubed dy. What you have to realize is that now that I have these limits of integration here, this just became a definite integral. That means the answer to this problem is going to be a number, not a function, not a family of functions, right? But again, this is in quotient form, and I have no quotient rule. So I'm going to go ahead and divide. Go ahead and just do the division. Y over y cubed is a y to the negative 2 power. 5y to the 7th over y cubed is a y to the 4th. And there's the dy. Now doing the integration. Bump the power up by 1 and divide. And the integration. Bump the power up by 1 and divide. And on this one, when I divide, the 5 disappears. Okay. And am I going to put plus a constant of integration? No, I am not. This is a definite integral. I'm simply going to evaluate from 1 to 2. And the evaluation is something you should be able to handle. You should be able to put those numbers into your calculator and deal with that. All right. But again, you will have to remember your trig. You simply will have to remember your trig. A prime example of that, integral from 0 pi over 3 of a sine of theta plus a sine theta times tan square theta over secant square theta d theta. Okay, for this one, you're not going to be able to just look at this and say, oh, I integrated something one time and got that answer. That's not going to happen. So 1 over secant squared becomes cosine squared. So I'll bring it up and multiply by a reciprocal instead of dividing. Tan squared of theta is sine squared theta over cosine squared theta. And again, the d theta says theta is the variable, nothing else is. Then we'll simultaneously factor out a sine theta and multiply in the cosine squared. When I multiply it in over here, it cancels this one. And so there's a little bit of trig you needed to remember. You need to remember your quotient identities, okay? And here, you have to remember that sine squared plus cosine squared equals 1. And now finally, we can integrate. Derivative of sine is cosine. Derivative of cosine is negative sine. So we got to remember to throw in that extra negative sign and evaluate from 0 to pi over 3, which again, I will leave that to you. All right. Now, one other theorem that we see in this section is the net change theorem. And the net change theorem says that the integral from a to b of f prime of x dx. In other words, if you're integrating something that is already itself a derivative, that's going to be f of b minus f of a, and the theorem goes on to say that f of b minus f of a represents the net change, not the total change, but a net, all right, a net value instead of a total value, okay? Prime example of that, if v of t, if velocity at time t for some object in linear motion is equal to t squared minus 2t minus 8, and this function is valid for t's from 1 to 6, and your 1 to 6 would be seconds. And it wants to know, find the displacement over that time interval. Displacement means not how far you traveled, but how far away from your starting point you happen to end up. In other words, displacement means what is your net change in distance, meaning if you went out 10 and came back 7, your net's only 3. You only ended up 3 away from where you began. So I would integrate this, and from 1 to 6, I'd integrate the t squared minus 2t minus 8 with respect to time, all right? I'm going to do an integral there, again, because this is a net, all right? This is a net change, all right? And remembering the integral of velocity is position, so I am correct that it's going to be a net position change. This is going to be a t cubed over 3 minus a t squared minus an 8t, all right? Now, if you were to evaluate this from 1 to 6, and again, I'll leave the evaluation steps of the process up to you, all right? You evaluate that from 1 to 6, and that will tell you net distance traveled, all right? Not total distance traveled, but net distance. Now, on the other hand, if you want to know what was the total distance that was traveled, then what you would need to do is take the t squared minus 2t minus 8 and set it equal to 0. I'll hope that this will factor. That would be convenient. Let's see, minus 4 plus 2. Right, so that gives you a t equaling 4 and a t equaling negative 2. Our time frame is from 1 to 6 seconds, so that's not relevant. So basically what happened is this thing came to a stop at time 4 seconds. Now, if you take your calculator and you look at the function, I'll put it in as an x squared minus 2x minus 8. You look at the table, we can verify that at time 4 it was stopped. Okay, so what was it doing the rest of the time? Well, in the time interval from 1 to 4, we'll put in, say, maybe a 2, and that tells you from 1 to 4 seconds. All right, from 1 to 4 seconds, if from 1 to 4 seconds, it was traveling in a negative direction. Negative direction just means in an opposite direction. All right, at time maybe 5, it's traveling in a positive direction. So for 1 to 4, it's traveling in a negative direction. Okay, from 4 to 6, it's traveling in a positive direction. So if you want to know total distance traveled, you would simply integrate from 1 to 4, the t squared minus 2t minus 8 with respect to t, and you take the absolute value of that answer, plus you would integrate from 4 to 6, the t squared minus the 2t minus 8, and it wouldn't hurt to take the absolute value of that answer and add them together. All right, now we've already done the integral. Okay, the integral is complete, did it right here. So evaluation won't be difficult. And for this one, I'll go ahead and evaluate. We're going to take the t cubed over 3 minus the t squared minus the 8t and evaluate it from 1 to 4. Well, calculator can help with that as well. Clear out that, put in an x cubed over 3 minus an x squared minus an 8x. Go to the table, evaluate it at 4, evaluate it at 1, and you're going to get a negative 26 minus a negative 26, and that would be a 2/3, negative 26 and 2/3, minus a negative 8 and 2/3. All right, and let's let the calculator help with that. Negative 20, no, let me put the negative out front. Negative 26 plus 2 over 3 is a negative 26 and 2/3. Minus negative becomes plus a positive. Plus an 8 and 2/3. You get a negative 18. All right, so what this means is it traveled 18 units in the opposite direction. Well, I'll take the absolute value of that because I want that to be represented as a positive value. Okay, plus over here, I will take the t cubed over 3 minus the t squared minus the 8t and evaluate it from 4 to 6. Okay, go to the table, and at 6, it's at negative 12. Okay, minus the 4, which is a negative 26 and 2/3, but minus and negative comes plus a positive of 26 and 2/3. So I will take 26 plus 2 over 3, which is 26 and 2/3, minus the 12, and I get a 14 and 2/3. All right, so 14 and 2/3 plus 18 is a 32 and 2/3. All right, so this thing traveled a grand total of 32 and 2/3 because I took the negative direction, made it positive, and added it to the positive direction. And that will be actual distance traveled when you disregard the fact it's moving in different directions. All right, so there is your definite integral and your net change theorem.